Good morning, everyone. Welcome to the second day of our ICAS Congress in Florence. I think we had a wonderful welcome reception yesterday, and maybe it became late before everyone come back, but I'm happy to see that we are so many here directly in the morning. The coming hour, we will have the IFAR ICAS General Lecture, and it's composed of short presentations, Q&A session, which is done a little different from what you're used to, perhaps. And then there will be an MOU signing at the end of the session also. So I think we will get started directly. And first I would like to welcome Bruno Sainjon. Bruno Sainjon is the chairman and CEO of ONERA. He's also the chair of the IFAR organization, and he will give a presentation on the IFAR organization as such. Then we have Markus Fischer, who's sitting over there. And Markus is the division board member aeronautics at the German Aerospace Center, DLR. Then we have Michel. Michel Pearce, he's the Chief Executive Officer of the Netherlands Aerospace Research Center, the NLR. Then we have Antonio Blandini. He's the president of CIRA, the Italian Aerospace Research Center. And then we have Bob Pearce, and Bob Pearce is Associate Administrator for NASA's Aeronautics Research Mission Directorate. And finally we have Reginald. Reginald Tan is Executive Director of Science and Engineering at the Research Council at A-STAR in Singapore. And we selected to keep it short with the CVs, but I think you all can trust me that they have impressive CVs, all of them. So we want to save the time for what's coming up. And to get the flavor of the Q&A session, I don't know, are we finding the slide here? No, those are not my slides. Well, we will do the Q&A in a setup where a general question is asked, and the panel has to answer yes and no by showing a green or a red sign. And I'm sorry that we are not covering for color blindness here, but we do our best to represent that. But we will also ask the question to the audience, and Adele will make an estimate on how the yes and no will distribute between the questions and answers. So the first question is, will we be able to increase traffic and decrease environmental footprint substantially by 2050? So we had it on the slide as well, but I repeat it. Will we be able to increase traffic and decrease environmental footprint substantially for aviation by 2050? So we start to ask the panel, do you think we will? Maybe it was a too obvious question. And then we ask the audience, if you think yes, you raise your hand now. Thank you. And if you think no, you raise your hand now. So what is your estimate? Okay. So it's 90% optimistic. That's perhaps nice for the community we are, and definitely our ambition. So Having said that, I hand over to Bruno to do the first presentation.
So good morning, everybody. It's a pleasure to be here for the second consecutive time after Stockholm for the ICAS IFAR lecture. As chair of IFAR, current chair of IFAR, I will tell you a few words about who we are and what we do, and as chair and CEO of ONERA, a very, very quick overview of our ATM activities, because I have 7 minutes to do that. So let's start. And let's start with IFAR. This slide shows you that the adventure began in 2011. The next one shows you that now we are now 26 active members. You see covering the whole planet, more or less, and we regroup 40,000 researchers. But members of IFAR means mostly public national research entities in our countries. Here you have described what we call the 4 IFAR's core values or pillar, which will be described in the next slides. The first one shows you how we work. Every year we meet in what we call IFAR Summit. It lasts 1 week, organized by one of the members, where IFAR principals meet. As you've heard with this panel here, most of us are heads of our organization. Every 2 years, we elect a new vice chairman. The previous vice chairman becomes chairman, and both of them, and the previous chairman, and the IFAR founder, and the DLR who acts as the permanent secretariat for IFAR, constitutes what we call the leadership team. You can see here, I will of course not detail them, the 12 working groups that we've created, which are dedicated platforms led to the disposition of our researchers and who can exchange on web conference and so on. End of last year, we created here in the last summit, which was in Napoli, we created a new tool called IFAR Research Projects. Beginning of this year, we branded 2 projects. You can see the first one here. It regroups DLR, NASA, and NLR who are there on this platform, and also our Canadian and Japanese NRC and JAXA friends under the coordination of ONERA. And the other one is here. It's coordinated by CIRA, our South African member, and includes CIA in China, ICAS in Romania, and CIRA, of course, here in Italy. For us, human resources are very important. So we spend some time of our discussions during the summits on human resources problems. And we have also created what we call the ECN, Early Career Network for our young researchers, because we, of course, think that they are the future of our establishments of activities. They are able to meet regularly through web conferences, but we sometimes create some events. And you can see here 2 pictures taken during the last event, which took place during the Le Bourget week last year, and 38 young people coming from 18 countries, 18 members of IFAR came here, and the next IFAR ECN event will be next week in Napoli. I will hand by 2 international partnerships we developed throughout the years. I start with the youngest. It was ICAO. It started in 2020. We had a lot of technical discussion with them according to their needs about UAM, and we produced to them last year a report, and have a lot of exchanges since then. They have us now to work on different new topics, and also you can see on the right part of this slide, very recently we learned that IFAR was included in a list of special international partners for ICAO events. And of course, last but not least, ICAS, it's the oldest partnership. We signed it in 2014, and this partnership will be renewed at the end of the present session with the signature of a new MOU. The next slide is a transition one. It introduces air traffic management, and you can see the actors, the levels to reduce aviation climate impact, the research axis, in order to introduce what my colleagues and friends will show after that. And my 3 last slides very rapidly describe what is done in France and what is done by ONERA. I said in France because I know that Markus, Michel, Antonio, who speak after myself, will speak about European cooperation. Of course, ONERA is involved, so I chose to give a few details about what is funded in France under the DGSE leadership. For the quantification, let me speak about clean aviation. We've been tasked by DGSE to regroup scientists from different organisms and disciplines to be able to work and know more and more closely and things like contrails. No more details. I know that Markus will tell you about what's happening in Germany. You can see on the right part the mention of a decor, which is a very new project. The announcement has been made last week and it's led by Thales. All this data coming from all these different tools and so on, we use in a new ATM that we have lab that we have created, and we use that to be able, with the help of artificial intelligence, to develop more and more accurate predictive tools. My last slide, as I spoke of AI, will be concentrated on the first line with Synapse. We've been working closely with the GSE air control navigators to air controllers and developed with them a tool, a software called Synapse to help them to make their decisions during the day-to-day traffic activities. Synapse is now operational on the five sectors which divide the French metropole in terms of aerial transport. 7 minutes. Thank you very much for your listening.
Thank you, Bruno. And then it's time, perfectly on time, actually. And Markus, it's time for you.
Yes, good morning, ladies and gentlemen. I would like to do the same as Bruno to speed up. I would like to give you a brief insight what DLR is doing in terms of using ATM for more sustainable aviation. And the material I'm presenting here is taken from our research groups. And so let's start with this. So the climate impact on aviation, you know it, is not just CO2. It's based on two components, is CO2 and non-CO2. And you see it here. So this is a pointer, yeah, here. You see the global warming potential over the time scale 20, 50, 100 years. And even if the pieces of the cake are varying, depending on which observation you use, you can say roughly 50-50. 50% is created by CO2, the other 50% created by non-CO2 effects. Other gases like NOx or methane or ozone, and the majority is given by the contrail cloud formation by our contrails. And you can, on the right-hand side, you can see what can you do against it. Mainly three areas, working on the technologies, not just on the engine in combination with sustainable energy carriers, but also on the airframe. You can work on, or you have to work on the atmospheric physics, because all the emissions do something with our upper atmosphere, and you can work on ATM. This is the gravity of my presentation today. And I would like to give you some examples of recent projects. The first one is a series of projects. It's called, it's a combination of the project ECLIF and Volcan and other projects which we are running with these partners you see on the right-hand top. And basically we are flying with one aircraft in front, which is burning SAF, sustainable aviation fuels, by a drop-in means, so stepwise increasing the level of SAF. And we run it with an A350, with a single-aisle aircraft from Airbus, but also with our A320 from DLR. And we are chasing or following these flights in the near field of an aircraft by our flight test aircraft, the Falcon, which is heavily equipped with atmospheric probes and measuring exactly what's what's emitted and how does it impact the upper atmosphere. And one of the major results you see here on the left-hand side, this shows really the soot particle emitted. And on the ordinate, you see the ice particle which are formed as a consequences of this, which is the basis for the formation of contrail cirrus clouds. And you see here on the first point is starting with the EIE engine from the A320. And you see here the effect of increasing the mixture by SAF up to 50%, how much you can reduce the number of soot particles, and at the same time, the same order, the number of ice particle. If you take a more modern engine like the Trent XWB, you see the engine effect, and here on top the SAF effect going up to 100% SAF, which has been flown by the A350 on both engines. So it could be shown that this is a good thing to do, and it has two effects. You are working on CO2 and at the same time on non-CO2. What can you do on top? You can route an aircraft differently than what you are doing today. So, for instance, this is based on a simulation which our researchers has done. You see here in the upper row that the red areas are predicted areas of climate sensitive regions where cloud formation can take place, and this is a standard route you would fly, and you can now circumnavigate by flying a little bit deeper, lower than the area, and going back to the original altitude, or you can continue in a standard way with your altitude. And this shows then on the right-hand side what kind of impact it has. This is the starting point. The non-modified activity was 1. And then if you do it really smoothly and avoiding this area, you go to this point 2, reducing by this time nearly 80% of these effects, and spending really less additional DOCs. And if you flying a standard curve, you are going up again and spending more DOCs, means mainly fuel. Another example which I would like to show you quickly, it's a bit animated. We are flying currently in Germany the 100 flight trials with 4 airlines over in the upper European aerospace. And you see here the prediction on the left-hand side of the daily sensitive regions where cloud formation can take place. You see how dense our airspace is. So you have to find opportunities to reroute these type of aircraft, and it is possible. We observe it at the same time with satellite data. And here's one example where the airlines are starting to deroute, and in the end you see the positive effect by the airlines that this has been avoided. So this is not for free because this creates a lot of workload on the air traffic control, and we are covering this topic as well by trying to give the air traffic control the flexibility. And as one example, you see here the Karlsruhe upper space area, and with the sectors, you see it here. And if one sector is heavily loaded, because you have, for instance, some persistent cloud areas here, you can increase, for instance, the flexibility by giving the chance that such an aircraft can be flight-centric routed, means one controller takes one aircraft and leads it through all the sectors. Usually, one controller has a license for one sector, and here's the idea that such a controller can lead it through all the sectors. And at the same time, what Bruno also said, we are trying to support ATC, the controllers, but also the pilot by by supporting systems. So this all goes into optimization loops we are running at DLR. You can see here what is important. At the same time, you are optimizing or you're running a sensitivity analysis where you see that you have to balance between capacity, productivity, noise reduction, climate protection, and so on. And you have to find an optimum, but this is feasible today. And yeah, many thanks. It was just a brief insight, but I'm happy that I could have the chance. Many thanks.
Yes, good morning, everybody. Let's see how this works. Thank you. Okay, we already had that. A couple of examples now to elaborate a little bit on the research we are doing in Europe, but also in close collaboration with other partners throughout the world. Sustainable aviation, that's the name of the game. We are all working on that. I think it's an open door, as we call that in the Netherlands, that in order to achieve sustainable aviation, we're not only looking at the airspace, but also ground-based operations in the airport and the aircraft itself. And I have four examples, which I touch upon very briefly, what we do in that manner. Okay, there are in Europe, and most of you know that, of course, there are two major aerospace or aviation research programs. The first is Clean Sky, Clean Aviation, dealing mostly with the aircraft itself, propulsion, etc. And the second, very important, is CIRA. And it's the third version of that, CIRA 3. And if you look at the mission of CIRA, the objective of CIRA is making Europe the most efficient and environmentally friendly sky to fly in the world. Well, that's very nice. Within CIRA, a large number of individual projects are being executed. I will touch upon 4 projects: Ciconia, Green Galer, Dinmars and Stepless, and only very briefly, of course, given the fact that I have only 5 minutes, and Adele is looking at me very closely in order to keep my time slot. Okay, well let's take the first one, Ciconia, and my colleagues are always very creative in defining what a good acronym is. So I wrote that down. Ciconia stands for Climate Effects Reduced by Innovative Concepts of Operations. Well, you could guess that, of course. So basically, what you can see here on the slide are the 4 steps, the 4 sub-projects which are being executed. In order to have a most optimally, from a sustainable point of view, flight trajectory, of course, you need a very good an advanced weather data forecast. You can see that a little bit depicted in the top left part of this slide. It goes without saying that this project is executed with close collaborations with the regional Met offices, because they are the expert in that field. Then the second part is to try to predict what the climate impact will be when you fly a certain route to your destination. Goes without saying that the coordination between the air traffic controllers and route planners is very complicated, because it's a multi planning process, and if you have found a environmentally friendly route, then of course everybody wants to fly there, so then you get separation issues, etc. So that's point 3 of this slide, to define the concept, a viable concept of operations to mitigate those impacts. And of course, last but not least, not to make it a purely theoretical exercises, then we complement that with actual flight trials in order to see what the real operational benefits will be. Okay, and next one project is Green Gear. Green Gear is green operations with geometric altitude and advanced separation and route charging solutions. The bottom line is, if you look at the vertical separation, aircraft fly with barometric altitude. That's their main means of vertical separation. Well, this is a big change, because the idea is here that we change from barometric altitude separation towards geometric altitude. So basically, that makes it more dependent, of course, because in order to do so, you need a global navigation-based solutions. But the idea is that it has a number of advantages. The first one is that you can reduce the separation. That's now about between 1,000 and 2,000 feet. And the idea is, and of course we need some safety analysis for that, you can reduce that to approximately 500 feet, thereby increasing the capacity of the airspace. Another operational benefit could be is that you get rid of the transition altitude. Normally an aircraft takes off with local air pressure, and then, well, in the Netherlands that's about 4,000 feet. You transition to 1,013 hectopascal, and then all the aircraft cruising are flying on that barometric level. So those are the benefits, but of course a lot of research and safety assessments and flight trials have to be executed in order to make that happen. Next one is talking about the approaches. So the idea is that from top of descent you glide towards the runway. What you can see here, what normally happens is that an aircraft top of descent here, it descends, and then a step-based approach. Okay, it flies level. I'm sorry, this is on the left-hand side, of course, and then it descends further to the runway. The idea of this project is to have continuous descent operations and a full glide path towards the runway. So continuous flap settings, and in order to minimize the power settings and the flap settings in order to make optimal use of the energy of the aircraft. That's closely related to the fourth and last project. The idea, of course, you all know that aircraft have flaps, of course, flaps and slats, but I'm not now talking about flaps. And there are discrete flap settings. Normally there are 3 flap settings, and throughout the approach you select more flaps. The idea is to adapt the aircraft instead, that you don't have discrete flap settings, so 3, but more continuous descent settings. So during the approach, you can have the most optimal aircraft configuration to lose as minimum energy as you can, and use minimal additional power in order to glide towards your runway. So that's a very short overview of the activities we do in European level. Thank you.
Thank you, Michel. Almost on time. Antonio, please.
Thank you. Good morning, everyone. Okay. So I'll try to firstly answer a little bit the question of Gunnar's. Of course, we all know that aviation is a highly energy-intensive sector, and we all know that there is a goal that we have to reach. The European Green Deals, launched in 2019, aim for Europe to become climate neutral by 2050. And that happens even if the estimation are that there will be a considerable amount of increasing use of aircraft in the next years. The idea is that there will be, they will triple the numbers. So one way that EU has used is the emission trading system. You all know about this topic. There is a directive that establishes the emission trading system, and the EU decided to temporarily limit the system to flights within the European Economic Area to support ICAO global measure known as CORSIA. The EU has extended ETS scope until 2027 to include departing flight from EEA to non-CORSIA states, while ICAO has set a 2050 goal of net zero emissions. The restriction of the geographic scope of the ETS is extended until the start of 2027, because what will happen? The Commission will assess CORSIA to determine if it meets or not the Paris Agreement's goal, and if it has been strengthened with adequate international coverage. Based on the evaluation, the Commission may propose extended the EU ETS to include departing flight and exempting incoming flight if CORSIA is not sufficiently aligned with the Paris Agreement or lacks adequate third country participation. In this field, there is also a little, it's not that little, but it's a sub-subject, that is the ETS Innovation Fund, that is something that could be very important for organization to use this fund to reach this goal, but compared with other sectors that have technology that can in a faster way reach this kind of objective, the timeline and the constraint need some adaptation, because at the moment they cannot practically be used by subjects like research technology organization. So ETS could be defined at a global level, and if this happens, of course, we all know that aviation is an international business, so it makes not peculiar sense if ETS are used only within the EU or within the EEA. And IFAR could favor this extension of a pragmatic way in which global action can be implemented. Of course, there is also a work to do on ETS, EF timeline and constraint in order to let this fund be useful for subjects like research technology organization. ATM play for sure a crucial role in reducing the environmental impact of air travel by optimizing flight path, reducing fuel consumption, and minimizing delays. Just to make few references to some topic of ATM. Modern ATM system can provide more direct routes for aircraft. There is the flexible use of airspace that allow for adjustment in real time to optimize flight efficiency, reduce environmental impact, and increasing safety. Continuous descent operation allow to reduce fuel burn and emission, performance-based navigation, collaborative decision-making, and predictive tools and real-time data sharing. Of course, all these lines of contribution and many others that come from ATM are for sure a key for sustainable aviation. CIRA, the Italian Aerospace Research Center, is strongly involved in initiatives like CESAR. Michel before spoke about CESAR, so I don't have to give other words on it. But I can mention just some project, running project in which Italian Aerospace Research Center is involved. Jarvis, GIS, I will give few words in my 5 minutes on this project, but we have also other, like Astonish, that increase the situational awareness of the pilot and air traffic control, Anticipate and ATC TBO, but I see that my time is almost ending. So Jarvis is an AI-powered digital assistant that can give tool to traffic control in order to facilitate and make it quicker, safest, and of course even more sustainable all the work of the traffic control. And GIS is a little bit romantic too. We see like a geese, like a bird, an airplane leaves a wake of disturbed air, creating an updraft that led the following aircraft to use that path and reduce fuel consumption and make the flight more sustainable. So, which in my poor speech, what I want to say that IFAR can favor national roadmap alignment, push for international cooperation, supporting international implementation of ETS toward net zero emission aviation, and support also some practical things like adapting the current ETS-EF timeline and constraint to the needs of the complete aviation sector, including aircraft OEM and research technology organization. So thank you for your attention.
Thank you, Antonio, and Bob, please.
Good morning, everybody. Great to be with you today. All right. So in the U.S. and the partnership between NASA and the Federal Aviation Administration, the FAA, we've had a long-standing relationship on the evolution and modernization of the airspace system. Certainly, sustainability is a key element of that. Today, if you look at this little bit of a S-curve type timeline, we sit at having adopted a trajectory-based operation system, so next gen in the United States. So each element of the flight operates on a trajectory. There's still more work to be done, but we're getting towards those goals of optimization and trying to maximize efficiency throughout the routing. So we're getting to that point of efficiency and especially proactive planning that enables that efficiency. But as we move into the future, there's a lot of work to be done to think about how we start to integrate not just traditional airline operations, but new operations, right? Things like advanced air mobility, high altitude, long endurance aircraft. We're working on elements of high speed flight, supersonic and so forth. So there's a lot of varied performance that we'll see for the future. All of that needs to be accommodated. And we want to move towards a more collaborative future. And we want to move towards a future that can keep up with the speed of innovation. And so one of the fundamentals that we're looking at is to, in cooperation with the FAA, is to really look at how the system is architected. So FAA will continue to operate its central air navigation service provider role, but we can start to get a service-oriented architecture. We can start to federate architectures, what we call XTM, Extensible Traffic Management. So if we're looking at UTM-type operations or high-altitude, high-E traffic management operations or AAM-type operations, we can create an XTM to support those and then federate that to the more centralized FAA system. In addition, then we can start to move towards a digital backbone, right, that supports all of that. And that will allow us also to look at the flip side of the operation, or the other side of the coin, which is safety. So if we have that digital backbone, we can start to look at how we actually use all that information to ensure we have, on a predictive basis, on a prognostic basis, that we have safe operations going forward. So we can start to see where hazards or issues or risks are popping up, and we can start to solve those before they become incidents and accidents. So even as we integrate technology, even as we integrate more and more types of operations, we can also make sure that we're keeping up on the safety side, which is absolutely critical for the future of aviation. The other, and as we move out, and so that, that NAS 2040 gets you that collaborative, where we start to see more and more of these kinds of operations, and that's really the FAA vision for that midterm, and then we've got a vision beyond that, Sky for All, NASA does, that brings it all together, because as we move into that future, we can see the complexity is going to go up, right? The scalability is going to be required, and adaptability is going to be required to make all that happen. We can start, if you've got that digital backbone, you can start to think about things like total system performance, right? So, and an integrated trajectory model, so that not just, the standards of what's the aircraft vector, what are the time requirements associated with that vector, and so forth, but you can start to think about how you wrap in things like environmental impact, right? So what are your emissions? What are your contrail formation? Noise. You could think about wake vortices and so forth. You can bundle all that into a trajectory model, so that now as you think about total system performance, you can actually start to look at not just the efficiency of flights and the efficiency of the system of flights, but you can start to think about its impacts, and you can start to think about optimization around. Now, that's a very challenging concept, right? Because you have different players in the system, so what's optimal for one isn't necessarily optimal for another, but you can start to think about those concepts and play those games in the system. And again, you can start to, as we get to that level, we get more and more automated, and we increase the MLAI on that, right? We can then start to think about how you automate some of your safety functions as well. So we start to have in-time system-wide safety. So we have mitigations that can be done in a more automated way, so that again you can continue to keep up with safety in addition to keeping up with traffic, and that's how we get to that 2050 state. So we're in the middle of doing this, and so you can see these are our kind of three key elements of the way in which we're moving forward within NASA. So I talked a little bit about that extensible traffic management. We've done UAS traffic management, and now we're moving towards AEM type traffic management and so forth. We're working on high E traffic management, where you've got high altitude, long endurance aircraft and so forth, potential for supersonic aircraft and upper E. And so we're working on those as things that you would federate into the traditional air traffic system that FAA operates. That digital services environment, I'll talk a little bit more about that, but the idea of now we can roll applications onto that digital environment, and we're doing that already with the airlines, through the airline operations centers. And then, again, that notion of in-time aviation safety management, where we're able to prognostically look at the challenges arising in the system and mitigate those before they become incidents and accidents. And so relative to more on the sustainability side, and those digital services, today we've got, if you look at that first block there, in yellow, the pre-departure planning, we've got that operating in Dallas-Fort Worth, and it's being extended to Houston. And essentially, if you think about Dallas-Fort Worth, it gets a lot of convective weather in the summertime, so lots of thunderstorms, those kinds of things. If your planned departure route is a thunderstorm sitting over that, you'd actually like to figure out how to get around that and not just sit on the tarmac. And so we've got a tool that does that pre-departure planning, that actually looks at what are the other conflict-free trajectories that might be out there, and do they actually give you a benefit? Do they give you a time benefit? Do they give you an emissions or a fuel benefit and so forth, rather than waiting on the tarmac to take off? And so that's actually in operation, full-time operation. It's flight trials, but with American Airlines, Southwest, others are actually using it full-time, and they love it. And then from there, we're moving on to these others, actually taking different elements of the trajectory, as well as things like, as you can see down the third line down, how do you deal with operations recovery, and then finally a capstone where we actually put together the entire 4D trajectory and operate as an overall, a fully integrated trajectory management. And now, again, you can get back and see how if you've got, a common trajectory model that has all those pieces, optimization actually can take different forms, which I think is really interesting. And that's it. Thank you so much. Appreciate it.
Thank you, Bob. And Reginald, please.
Good morning, everyone. I'm from Singapore, and if you have been there, you'll know that we are a small island country, and therefore our air connectivity is vital for moving of people, of goods, for our trade and our businesses. The Singapore Changi Airport is subject to the same competitive pressures of cost and efficiency, climate sustainability. So we, common with all the previous speakers, are doing R&D on sustainable ATM, sustainable airport, and sustainable airline. So those are the themes, the 3 A's. Today we talk about ATM, so very quickly. Demand capacity is predictive tools to support decision-making, performance-based navigation to optimize direct routings and descent profiles to reduce fuel burn. And gate-to-gate, we mean trajectory-based operations to optimize departure intervals for our airport. Singapore's Civil Aviation Authority has embarked on an ambitious aviation transformation program to enhance strategic ATM and regional cooperation. And A-STAR, my organization, is collaborating with our CAAS to make this happen. In terms of weather, we've heard quite a lot this morning. Convective weather modeling and prediction, particularly important for our humid tropical climate in Singapore. We're building Aeromet models for different regions, for aerodrome, for terminal maneuvering area, as well as en route. I apologize for this slide. When I asked the researcher to describe their project, it just comes out too much. Let me summarize quickly. So we use a state of science weather data and forecasting models with our MET service. We then use physics-informed AI and multimodal AI to work on the data. And the aim, of course, finally, is to validate for real-world air traffic operations. I have a short 2-minute video. If it works, if it doesn't work, I will sit down. This is by one of our institutes, Institute for Infocomms Research.
The concentration of incoming and outgoing flights to and from a busy aerodrome often results in congestion in the TMA. To ensure the smooth flow of traffic, air traffic planners need tools that provide practical capacity estimates for pre-tactical decision-making to maximize resource utilization. The I2R Intelligent Transportation Solutions Division developed a practical capacity estimation tool that provides improved information support to air traffic management systems through fast-time simulation and machine learning methods. This tool deploys accurate physics-based and learning-based models to predict the possible aircraft movement in various traffic scenarios. Operational constraints, such as runway operating mode and direction, weather within TMA, separation requirements from the airspace, as well as traffic mix, and the air traffic controller's workload, have been taken into consideration. Based on these variables, the practical capacity is determined with these 4 steps. End users can select indicators on the tool to simulate the required scenarios and generate the results accordingly. Through the fast-time simulations and optimizations, demand profiles are created from history records to determine the practical capacity. A comprehensive and accurate prediction of all the different TMA entries, as well as operating runways, will be generated in a time sequence. The granularity can be specified by the end users, based on the needs of different use cases. This high-fidelity tool offers air traffic planners an accurate practical capacity estimation, which could help to shift from tactical air traffic control to a more pre-tactical and strategic air traffic management decision-making process. In summary, this tool aims to generate an accurate and comprehensive prediction of TMA and runway practical capacity, with the considerations for various operational conditions. It assesses the demand-capacity imbalance by analyzing performance decline, which allows planners to identify the necessary air traffic flow management or ATFM actions. It also supports trajectory-based operation by enabling more preemptive air traffic control or ATC actions. This could help to enhance safety, efficiency, and optimize the TMA and runway utilization. Besides the practical capacity estimation tool, the A-STAR team is working on other smart tools for the aerodrome and air traffic management. We aim to assist aviation transformation through the creation of these smart tools that leverage on rich data to provide better information support for the next generation air traffic management systems.
This is my last slide, just to inform the audience that the IFAR annual summit is held every year in October, and we are very proud that this year they will come to Singapore. So IFAR will be in Singapore, and the added bonus is we will have Dimitri, who is accepted to come. So I hope this will be enhance the closer cooperation between IFAR and ICAS. Thank you very much.
Thank you, Reginald. We are, of course, not on time, but not too bad. So I think before we go into the MOU procedure, I would like to see what we have for position in the audience first. And I think we go with question 2 here. Will aircraft be allowed to fly predominantly unconstrained optimal routes in 2050, and linking to several of the presentations here. So I will ask the audience first. If you agree, raise your hand for a yes, no. Yeah, yes, no. Okay. For a no. So what have we got to then? Yeah. And then the panel. Can you give your verdict? I must say we struggled to find questions where we would get different answers, and I was pretty sure for this one, but maybe you should ask Markus, why do you show red? Yeah.
Yeah, I think this was a plan to present it, that this CO2 is not the only source of pollution, and yeah, you see it just visibly. That's the formation of clouds caused by air traffic is really another big impact, and therefore we would be not well just to focus on CO2. No? So there's really something else. Yeah. Okay, sorry. Okay, but then I just continue for the second part. Is because of this, of course, we are working heavily on these climate compatible routes. Let me say it like this, and you should know that. Nearly 80% of these effects, of these non-CO2 effects, is caused by 6% of worldwide air traffic. So it makes really sense to concentrate on this 6% of flight routes. And also what Michel said, I think we should be capable by then in order to reroute then the aircraft in order to become climate compatible.
Yeah, fully agree. I dare to say that in 2050, we're talking 2050, that all the tools are more or less available. A very accurate meteorological prediction is available. The problem I see a little bit, it's more political, because if you have an optimal routing with respect to the environment, then it could very well be that you fly less over certain areas, and that could have a political impact, and that's something we as applied research organization cannot influence.
Maybe if I can complete with something else and environmental aspects. Of course, there are a lot of works which are done throughout the world to give more freedom for air companies to plan the flights. For example, in Europe, we have something which is called free route in order to do that. But we have to take into account that there will be some constraints which will remain. The high density of the traffic, of course, the need to keep the very high level of security and safety that we have in the air traffic, and also some very practical limitations, like, for example, the airport constraints, the airport capacity will certainly limit the possibility to give a predominantly unconstrained optimal routes to companies.
Okay, thank you, everyone. I'm sure we can continue to talk about everything that was presented here, and I think you know that there are detailed presentations on most of the things that's being mentioned in this session, so Q&As will be possible in these sessions as well. But by that, I think we should thank all the speakers again for their contributions. And now we will continue with the MOU procedure, and I'm not fully clear here. Will you start, Bruno?
Yes, thank you. Just a word of introduction. As I said earlier, a partnership between IFAR and ICAS is our oldest one, 2014, so it means that we have now entering 10 years. All of us who have children, we know that we are entering their teens, we have to reframe them. So it's about also time to reframe our cooperation. But no, most seriously, the way to proceed has already started. Those who were there yesterday could see that we had 2 IFAR sessions yesterday, one in the afternoon about wildfires, and one in the morning about AM. And for me, it was a pleasure to see the same young people who were on the pictures I've shown you in Le Bourget, showing what they've done on AM, and thanks to ICAS to have allowed that. And that's exactly the aim of the MOU, to develop the cooperation between ourselves, as Reginald has said. It will be also obvious, tangible in Singapore, and that's why the MOU that we are not going to sign is going to say so. Thanks to everybody. We are entering the procedure of the signatures. I'm just trying to find, Adele, where the things are. One last thing, at the end of the signatures, you will be allowed to enjoy your first break of the morning, and we will make pictures. As I've seen that there are a lot of people here from the IFAR family, please be free to please stay with us, and we'll make a whole IFAR family pictures in order to show that it's all IFAR that is behind this partnership with ICAS. Thank you. Thank you very much. We managed to keep the time, which was not.
All right. So, on behalf of ICAS, we are a couple of more minutes, okay? On behalf of ICAS, we're very proud to continue this ongoing relationship. It was part of our strategic plan many years ago to kind of unite the world, and we thought that this would probably play in three axes. One was the union of all the research organizations, and Joe Zodra at the time, who was also a president of ICAS, and at the time head of DLR, was able to plow through, and we're very glad that this relationship is perhaps the most successful collaboration we've ever had. The second one was around the axis of the CTOs of the various organizations, and that went off and got started also. And then the next one for us is the global network of all the universities. So we're very, very proud to be part of this family. We're looking forward to a very long relationship with you.